Good morning, everyone. My name is Arturo Pascuzzo, tenure track assistant professor of Pegasus University from Naples. The work that I'm going to present today is about a novel finite element modeling strategies based on the use of the movie match technique to reproduce dynamic crack propagation mechanism inside brittle materials. This work is co-authored with Professor Francesco Fabbrocino of Pegasus University and the professors Fabrizio Greco, Paolo Lonetti, together with the Dr. Domenico Ammendolea from the University of Calabria. Okay, here there is the summary of the presentation. The presentation is structured in 5 parts. In part 1, I will explain the motivation of this work. In part 2, I will resume the theoretical background at the base of the proposed numerical model. In part 3, I will discuss some aspects concerning the numerical implementation. And in part 4, I will show you some interesting results that we have obtained by the application of our methodology to the analysis of some relevant benchmark case. And finally, in part 5, I will outline the main conclusion of the work. Okay, let's start to say that all materials have imperfections, I mean internal cracks. And these internal cracks propagate when the material is subjected to an external action. In particular, the crack propagation mechanism is dynamic in nature, and in the case of brittle materials, internal cracks propagate at high propagation speed. And sometimes an original propagating crack can split in multiple crack fronts. And this phenomena is known in the literature as the branching phenomena. And here you can see an example of crack branching occurred in a space membrane of 1 meter 100. So, as you can imagine, simulating this kind of phenomena using a numerical method could be a very challenging task. And in the literature, you can find many numerical methods that tackle this problem. Here, I try to broadly classify this method according to the way they represent the crack. So you can find the smeared crack approaches and the discrete approaches. Smeared crack approaches account for the presence of crack at constituent level. I mean, this method in the regional crack reduce the elastic properties of the material. An example is the phase fill method. On the other hand, discrete approach represents the crack as an internal geometrical discontinuity. An example are models based on the cohesive zone models, and these models offer a very accurate representation of cracks. However, each method, regardless that it belongs to the class of smeared crack approaches or discrete approaches, has advantages and disadvantages. So currently, it is impossible to identify the best numerical method that ensure accurate results and at the same time high computational efficiency. During the last year, many efforts have been spent to develop a novel class of numerical methods, the so-called hybrid methods, that combine the standard procedure to take the more advantages while reducing the main drawbacks. So hybrid methods are very promising and could be considered as the future of the computational fractal mechanics. So in this framework, we have tried to develop an hybrid method to simulate dynamic crack propagation mechanism inside brittle materials. In particular, the proposed method has been developed within a standard finite element code, augmented with the use of the multi-mesh technique based on the arbitrary Lagrangian linear formulation. And this technique is used to reproduce the geometry variation of the computational domain because of propagating crack. In addition, we have implemented the interaction integral method. This method is used, the proposed method, to evaluate essential fracture variables, I mean the dynamic stress intensity factors that are essential to evaluate the direction of propagation and also the crack propagation velocity. So before introducing the Godin equations at the base of the proposed numerical method, it's useful to explain some basic concept at the base of the Arbatì-Lagrangian linear formulations. The use of the Arbatì-Lagrangian linear formulation introduced a novel system of coordinates that coexist with the traditional material and spatial frame. The novel system is known as the referential system, and the referential coordinate identify the spatial position of the nodes of the computational mesh. And each system, I mean the material, spatial, and the referential system, are linked to each other by means of a proper set of mapping functions. In addition, the use of the ARE formulation requires that all the governing equations of the problem under investigation should be stated in the referential system. This means that traditional governing equations, for example, of the solid mechanics that are expressed in the material frame, should be stated in the referential system. If we consider that these equations contain gradient operators or first-time derivatives, these operators should be stated in the referential system. So we can use these expressions, relationship, that link the gradient and the first-time derivative from the material to the referential frame. So taking this expression in mind, we are now ready to introduce the governing equations at the base of the proposed numerical methods. In particular, we have two sets of governing equations. The first are the governing equations on solid mechanics. It is expressed in weak form with respect to the material frame. So using the above expression, we are able to define these governing equations in the referential frame. The second set of governing equations are those associated to the moving mesh problems and govern the cinematic of the movement of the computational nodes. And this method, these governing equations, are generally known as Rezooning methods. And here we have used a Rezooning method based on our plus approach. So we have to solve these differential equations under proper set of boundary conditions. In particular, we use a boundary condition that imposes that the computational node around the boundary of the computational domain should be fixed. And here there is another boundary condition that imposes at the computational node associated to a crack tip to advance in the direction of propagation and with a certain crack propagation velocity evaluated using proper fracture criteria. Another important concept is the use of the interaction interval method. The interaction interval method is derived by the application of the traditional J-interval expression to a superimposed state formed by the combination of the files of the problem under investigation, I mean the stress, displacement, and deformation files, and auxiliary files for which stress intensity factors are known. So the application of the J-integral to these superimposed states provide three terms, and the mutual term is known as the interaction integral. And this is the expression of the interaction integral with reference to the material frame. And also this expression should be stated in the referential system. So to evaluate the dynamic stress intensity factor of the problem under investigation, one has to evaluate two main integral expressions. The first is associated to an auxiliary file of PUD mod 1, and the second to an auxiliary file of PUD mod 2. So we get two values of interaction integral, and these values allow us to evaluate the dynamic stress intensity factors of the problem under investigation. Okay, how the proposed model evaluate the direction of propagation? We have used the maximum of stress criterion developed by Erdogan and C, and this criterion provides this expression of the kinking angle that defines the direction of propagation, and also this equivalent stress intensity factor that we have used to define several fracture functions that govern the crack initiation instant and also the crack growth process. And these functions are defined in terms of some material properties, I mean the dynamic crack initial toughness and the dynamic crack growth toughness. In addition, we have introduced fraction functions that define the instant of crack branchings. In particular, the proposed method is quite flexible to implement or fraction functions based on the velocity criterion. I mean, when the crack propagation velocity reach a critical value, crack branching events occur, or fraction functions based on the critical value of the stress intensity factors. Okay, now I show you some aspects concerning the numerical implementation. We have implemented the proposed method within a standard finite element code, and we have developed an algorithm that manages the propagation process automatically. And here you can see a flowchart that summarizes the step followed by the proposed algorithm to reproduce dynamic crack propagation process. At the end, the user should provide to the model basic information regarding the geometry of the computational domain and the material property. It is important that the computational domain or the geometry should be a pre-crack domain because we use the interaction integral method, and the use of the interaction integral method could be applied to a pre-crack domain. After that, the code starts to work, and initially it performs a geometric operation on the geometric entity that depict the internal pre-crack. In particular, add an additional node to the crack tip, thus forming a short segment that during the simulation will stretch in the direction of the propagation, thus reproducing the crack growth process. After that, the code mesh the geometry, and the analysis starts. In particular, at the beginning, for each time step of the simulation, the code checks the occurrence of crack initiation, and when these conditions are satisfied, the propagation process takes place. And the computational node associated with the crack tip advances in the direction of crack propagation. As you can see in this little animation, the finite element around the crack tip distorts due to the movement of the computational node. And this distortion is monitored by the algorithms. In particular, when the distortions of the finite element become high, a remeshing action takes place. So the proposed method, different from traditional finite element procedure that perform a remeshing action for each increment of the a crack. In this case, we perform a remeshing action only when the distortions of the finite element became excessive. Another aspect monitored by the proposed code is extensions of the stretching segment. In particular, when the stretching segment reach prefixed extension, the code arrests the analysis, takes the configuration of the geometry, of the mesh as a new geometry, creates another stretching segment, and restarts the analysis. Another thing is the control on the crack branching events. In particular, in this case, the code arrests the analysis and creates a novel geometry by inserting two segments that reproduce the splitting of the initial propagating crack. So this process continues until the total failure condition of the problem under investigation occurs. So let's view some results. In Italy, we have validated the Albertin-Lagrangian linear formulation of the interaction integral. So we have investigated this pre-cracked plate under tension. In particular, this is a particular case because for this case, the code doesn't evaluate the crack propagation velocity. The crack propagation velocity is imposed. And in this case, we have the analytical solution of this problem, in particular, the time history of the mode 1 stress intensity factor. And we have investigated this plate using different mesh configuration, and we have compared our prediction with the analytical solution and the prediction of another numerical model. As you can see, the proposed model is in good agreement with both the analytical solution and the other numerical method, regardless of the mesh configuration adopted. Here, there is another example. In particular, this is a pre-cracked plate under tension, but in this case, the proposed model evaluates the crack propagation velocity. This represents one of the most relevant benchmark cases that many authors have used to reproduce or assess the ability of a numerical model to predict a crack branching phenomena. In this case, we have adopted to check the occurrence of crack branching a velocity criterion. I mean, when the crack propagation velocity reached the 60% of the regular speed of the material, crack branching event occur. So we have compared our prediction with several numerical models, in particular models based on a phase field method and the periodynamic theory, which predict the occurrence of crack branching without external criteria. And as you can see, the comparison in terms of time history of the crack propagation velocity and the final crack path show that the proposed method is ensure accurate results. In this case, we have tried to assess the capacity of the proposed model with a more complex case, in particular this edge crack plate impacted by a projectile. This case is a case of mixed mode condition, and we have analyzed two impacted velocity. The first one is of 16.5 meters per second. In this case, we have no branching events, and the crack propagates along a trajectory inclined almost 70 degrees with respect to horizontal. In the second case, we have increased the impact velocity at 40 meters per second, and in this case, multiple crack branching events occur during the numerical simulation. At the end, we have compared the crack path predicted by the proposed method with a phase field method, and as you can see, the final crack paths are almost comparable. So just for concluding with this work, I've shown you a novel model to simulate dynamic crack propagation mechanism inside brittle materials. The proposed model combines a standard finite element code with a movie mesh technique and the interaction integral method. In particular, the results have shown that the arbitrary Lagrangian linear formulation of the interaction integral ensure accurate results, and also the proposed method ensure accurate predictions of simple and complex crack problem. And different from a traditional finite element method, the proposed method improve the computational efficiency because perform a remeshing of the computational domain only when the finite element distorts excessively. Thank you for your attention.